Hey, welcome back. This is part 3 of my video series, Wolves on the BackBit. And now we are 13 days into the project. I have my video playing to an acceptable level, enough to move on to the audio. And the audio, however, I was a bit too optimistic with what I learned from Jeff Burt and a little cocky. And I thought I could be able to get my clip to play cleanly on the Commodore. And unfortunately, that is not what was happening. So I was about to, well, as you're going to see from the clip, the big long half an hour on a tripod clip. But trust me, it's actually pretty entertaining. Probably one of the best of the bunch. What you're about to learn is I was about to try something else, but on a whim, I ended up exploring a different type of Digi altogether. One that I started to learn about in early 2021. Monstro Giganto was released, and it had some of the smoothest sounding digital audio I've ever heard. It had the smoothest sounding digital audio I've ever heard on the Commodore. And someone gave me a link, and it was done by, now I'm going to get his name wrong. I always get his name wrong. Hex Mahoney, this guy right there. And he's a freaking genius. He figured out how to coax these amazing noises out of the Commodore 64 SID chips, both varieties. And this is about 8 years ago, I think. He found, maybe 9? I don't know. He found a way to do the impossible. And at the time, I did ignore what I learned because it looked mega confusing and technical. And if you ignore all of the mega confusing technical stuff, getting it to work is actually pretty easy. And that's what I managed to do in one night. Even a year later, I still can't say with confidence that I've got it down. There are some drawbacks, perhaps. Some things that I still haven't got a handle on, and even to this day, I ended up patching. Well, I guess we're jumping ahead to the last video, never mind that. What you're about to see, yep, is one night's delight and experimentation and just me screwing around, and it was one of the most euphoric experiences I've ever had on the Commodore. Crazy stuff because it opened my eyes to potential. There is so much you can do with this, and well, digital audio is memory hungry, as everyone knows, but with the BackBit, that's not really a restraint anymore, because you think about it, with one BBT file, you can load up as much data as almost a PlayStation 2 video game. Like, not in terms of, quality and stuff, but that much data. A DVD, look at that thing. Most games don't even fill those up. A lot of them just, dumb down and use a CD, which only holds 700 megabytes. This whole project, maybe 12 megabytes. So I have so much more space that I could use. I could read you a story in digital audio if I wanted, but copyright would just pounce on that, wouldn't it? So yeah, never mind. But I'm just saying, digital audio and the BackBit are possibly the best bedfellows there could be. And so anyway, yeah. Okay, I keep talking. I'm just watching myself being majestic. Okay. I'll probably do that again. Please forgive me down the road as well. All right, let's get to it. Part 3. Here we go. And yeah, oh man, you're going to like it. I hope you're going to like it, or, well, whatever. You're going to like it. Let's do it.
This is great. I've been experimenting with the D418 Digis that I learned from Jeff Burt. And I have had some success. They sound pretty bad, although I did not use his own program that normalized or compressed them. I figured I could do better. Probably not. But I could see some noise in it. I was going to try running it from an NMI tonight, but I started chasing a different idea. Because earlier, what it was is I was just running it through just a simple loop. Interrupts were happening, the key scan was happening. You know, it was susceptible to all sorts of delay. And it sounded a little bad because of it. However, check this out. This is, yeah, right here. This is the, what do you call it? The Mahoney method here. This fellow is a freaking genius. So, what I did is I incorporated both of his tables. Well, at first I have a flat 64 here, so I figured that I needed this table, so I entered it. And this is, well, you've already stared at the screen long enough to know what these settings are preparing for. So here's what it sounds like. The screen on. No interrupt, well, interrupts are allowed to occur, and I'm using the 8580 table. Here we go. Now that sounded bad. So I figured, what if I had the table wrong? Well, sure enough, I did have a few entries wrong, but I fixed it. And then I entered the other table. I'm guessing I have the old SID chip. And the difference is, the second time I play it,
The water always tastes so good here. The water always tastes so good here.
oh, now it's not doing it. It used to would alternate between a quieter version and a louder version, a quieter and a louder. Both on their own were acceptable to hear, but one after another, you could tell that something was changing, and I still don't know why. But anyway, so let's stop interrupts from happening and listen again.
The water always tastes so good here.
You see, that's clearer, right?
The water always tastes so good here.
You can still hear some hiss.
The water always tastes so good here.
Let's disable the screen. Interrupts are off, and now listen.
The water always tastes so good here.
And it's actually a little faster because it's not getting stopped for all the bad lines.
The water always tastes so good here.
But my point
The
is,
water always tastes so good here.
besides how good the water tastes, I just don't want to have a Digi playing, even though this is it. I am embracing this sucker hard because this is so great. I can't believe the Commodore 64 can do this. I mean, the clip, well, okay, forget this. Let's go to the monitor. Yeah, I'm using this old monitor. I love this thing. Anyway, oops. This is the code itself. As you can see, there's a rough loop clearing out the SID. These are the recommended settings that I learned from, well, partly from Jeff Burt and Mahoney here. There we go. Set our buffer playing, or the data begins at 2000. And this is it. This is all it does. Grab a byte, switch it to the X register, lookup. This is an 8. The samples, like my Digi or whatever, is an 8-bit raw, unsigned PCM. I guess it's PCM. I don't even know what that means. 8,000 hertz, 8 kilohertz. So starting at 2000, it'll grab a byte, and the full range of 0 to 255 aren't even used. I didn't further process what Audacity gave a result of. I did follow Jeff Burt's Audacity tips. What he put there was brilliant too. He knew how to take any file, any audio file, and turn it into something you could load into the Commodore and play. Wow. So anyway, yeah, you've seen this already. Get a byte of the Digi, put it in the X register, look up in the magic table, spit it out to the volume register, a little bit of a delay. That's it. So we know that because of this delay, you're still able to do other things. If you had this running from an interrupt, or better yet, an NMI, you still have some free time to run a game or show graphics. And by the time you see this, I should have already been done what I planned to do. I was running into a bit of a soul-crushing roadblock when I realized that the audio was not going to be up to snuff. And tonight, now I know it can be. It's funny because I should be, yelling from the rooftops, but I just went, oh, now it works, and now I know I can trust this, and I'm happy. So anyway, grab a byte, switch to the X, look up the magic value, spit it out, and there it is, 8042, back it goes. Gets another one. And look at all these EEEs. I just filled memory with this when I was done. So after one page is done, bump the page, look for the end of the sample, that's it. And then it comes back to basic and done. Now, you want to see those magic tables? The first one was the 8580. I entered it first because I figured that's what this computer would need. So there's the code. That's it. And I originally had a bunch of crap in this program that I took out. That's why the table starts at 8200. But there it is. So, for example, suppose you had you probably won't, but if you had, say, a number 9 in your Digi, it just looks up this value, spits that out to the SID. And you can see a lot of them are duplicated. However, after that clump is gone, there will likely be no more 9Ds. It changes, right? Or 9Es. Now it's this, now it's that. You see all the difference. There is, maybe it's on the other table. I saw a 0 in here. I thought zeros were bad, but apparently not with these settings. Yeah. So, 8300. This is now the 6581 table. You notice it's a little different. Okay, now here, I'll show you how different. Let's say 8260 to 8290, 8360 to 8390. Completely different. So if you're running off the wrong table, you're going to get the wrong results. And I think I still have my source in memory. These lines are, I guess Mahoney refers to them as the magic settings. Whatever they do, they're set in the, I guess, what is this, the release time? Attack, decay? No, attack, decay, sustain, release. And that one, that's the pulse waveform, test bit, and go. This is the frequency of, or the, what do you call that? The pulse width, I believe. And this last one, this 3, only filters 2 of the voices. Whatever. I don't need to know why it works. It does. You can look on, maybe I'll post a link on the screen at this moment, but Mahoney describes in incredible technical detail. Holy crap, I will never understand it, but I do understand this works. And I don't understand why, but I'm happy with that. But anyway, let's skip it. Now this is what happens if you still clear the SID out, but you do not prepare to use the tables. Doesn't that sound like ass? Okay. Now we're skipping the part where we skipped over the part.
The water always tastes so good here.
Those settings are critical. The tables are critical. There's probably a way, I'm sure there is, to determine which SID you're running. At the moment, my plan is just to offer both and let the user choose, because if, I don't know, because I just don't want to mess with it. This
The water always tastes so good here.
Delicious water.
The water always tastes so good here.
Hey, it sounded different that time.
The water always tastes so good here. The water always tastes so good here.
See that? Loud one, quiet one, loud one, quiet one. I still don't know why that is. I actually added a delay between the time the SID was cleared and before the magic settings were put into place, thinking maybe the SID had to settle down. That didn't make a difference. So there you have it. This is great. And this, what you see here, well, you don't see much, but this conceivably can still fit on a floppy disk. As you can see, the code itself was incredibly small, and this isn't even like the best version of it. This is just crap because I'm using the monitor. I loaded stuff in directly to 2000. Oh yeah, let's look at the Digi itself. This is the Digi itself. Now, I started with a signed raw file. I changed it down to signed, and that's something Bert basically recommended, and it makes sense. We want 128 to become the halfway point, and as you can see, most of these values are hovering around there. Let's see here. Let's get rid of this RAM. Was it that one? I think so. So we want to count. I'm going to skip all the playback stuff. Where's my Go2390? Oh, I deleted a bunch of things. Oh no, 390's there. Okay, good. Okay, so now what is this? Another thing I skipped. See? That's how all those chunks didn't show up. Okay. Now all it's going to do is count all the bytes. There, it's already done. It counted the occurrences in my sample file. And there they are. This is the value, the number of times it occurs, and the running total of all. So far, my file doesn't even have any of these values in it once. Oh, now they're starting to appear. See, there's a few of them. And this was normalized in Audacity. Now, would it sound even better if I was able to stretch this to fill the entire range? I don't know. I haven't tried that yet. But as we get closer to the middle, you see the occurrences here are more and more. And sure enough, in the center, chunk-a-doo, look at this. Thousands, 10,000, you know, and it'll start trickling off. There's only about 24,000 bytes in this. They're not packed bytes, that's it. It's just 8-bit whatevers. And now we're almost nothing. And sure enough, starvation time. See, there's not a single value above 223 in the file. So it could be expanded. But would that make a difference in the audio? I don't understand normalizing. I don't understand loudness. I was following Jeff Bert's instructions, just boom, 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 because I mean, he got it to work. That was amazing. And maybe, maybe I've already showed you earlier in the video what it sounds like. Just a D418 volume settings, 0 to 15. Now, here's another thing. The regular Digi, all you're doing, feeding it a 4-bit number to the volume register. But it's not like that corresponds to anything, really. It turns out this just creates like a voltage-related tick. And somehow the magic happens there. However, the Mahoney method, he's discovered with the settings and trying multiple SID chips on the two varieties, he's figured out that if you give it those magic settings to ensure the maximum amount of variation spectrum, I guess, in these ticks, depending what value you feed that, you could get, you know, not one of 15 values or whatever, but oodles of them, all different. And that expands the range of the audio you can get back out. Doesn't expand it, it just doesn't hack it away as much. And yeah, these aren't compressed down into 4 bits each. They're 8-bit samples. But so what? They sound so good. You know? I gotta put this back. Let's get rid of that. What else? What else? Back to the playback part. Oops. Haha, that's why I had that rammed out. Okay.
The water always tastes so good here. The water always tastes so good here.
Man, that's great.
The water always tastes so good here.
Are you sick of listening to that yet?
The water always tastes so good here.
I'm not. But for fun, check out the delay. Change that. Ah!
The water always tastes so good here.
Basically, you are slowing it down, like playing a record slower. You could speed it up quite a bit. Let's just make this that. Okay, there we go. Haha, didn't fall for it that time. What? It sounds like playing a cassette fast. Man! That's cool! It's useless, but cool. The effect sounds so good. And of course it's a little slower because the bad lines are interfering. So it depends on whether you want to use this in a game or whatever. If you want the screen visible, account for that. However, there is a difference here. This isn't running from an interrupt. So when the bad line comes along, this is our bad line. When that comes along, the processor stops, doesn't care. So if it was counting down from 20 on X, 20, 19, and now it continues. This was wasted time. If you had an NMI doing it, say the NMI fires here, okay, good. Fires here, fires here, fires here. It'll happen here, but the next one will happen there. You didn't throw it out of whack. Does that make sense? You know? Because it's still keeping track. It's just knowing that once that happens, next available moment, do it. And the delay itself doesn't have to be software based anymore. It just knows when it's time to do it again. And I guess maybe that's what I'm trying to say. I'm not saying it very well. I'm sorry. It is 1:32 and 1:33 in the morning. Saturday, October 23rd, 2021. Yeah. Was this 20 before? See, I got rid of all that earlier crap I had. Okay, one more time.
The water always tastes so good here.
You want to know who's saying that, don't you? I wonder if I could show you. Nope, I got too many obscenities in my disk directory, so I don't even want to load it and list it. And I got no wedge in place, so I can't even cheat. The BackBit is currently, you know, sitting over here. This guy, he's, you know, hanging out. So I'm just running off of the SD2 IEC. Not that I needed that much storage, but man, you sure get hooked on that. The fact that I can just pop this sucker in and do what I want. Oh man, yeah, that's a keeper. This is now device 11. I know. And it's slow because I don't have Jiffy DOS. But that's not the point. When I plug in the Super CPU, even when it's at 1 megahertz, what? Oh yeah, because I've changed it so much. Duh. Okay, I'm sorry. Thanks for watching all this. I'm going to press stop now. You have a good night. Yeah, here's a little postscript. I was thinking, why does it play slower when the screen is active? Well, in this particular player, it's not run by interrupt. So yeah, that is why, because the delay is the delay gets paused. So by the bad line, and then it continues. In effect, because there are 1,000 bad cycles on a screen, 40 fetches, 25 rows deep. So yeah, overall, there's the math. It slows you down this much. But if you're running off an interrupt, bad lines will just mean less code happens in that time. Once the interrupt is, once the bad line is over with, the interrupt quickly does its thing, and the next one will occur a little earlier because the timer is probably, you know, partly there already. The next one is about to occur sooner than usual, and therefore you do not get any delay in playback, or it doesn't slow down. You know, I'm not really good at narrating when I got the camera running. I get really nervous. I'm sorry about that. It is now 2:12 in the morning. Oh, yes. But, yeah, basically what you see here, I typed it all in before I started the camera running. That's why, obviously, if you're just running like what I'm doing tonight, you saw it. It was just throwing bytes at the SID as pretty much as basic as you could. In fact, you probably could do this from basic. It would sound like absolute slow crap, but you could. But this was just to make sure I could make it work. And now that I know it's going to be, obviously it's going to be run by an interrupt, probably an NMI. I've got ideas, man. Oh, this is so great. Oh, boy, oh boy. Well, I guess I'll waste more of your time later after I actually get something working.